Alright, so this is notes on the beginning of Zoomdoll Chapter 3. Zoomdoll, if you haven't figured that out already, is our textbook. I'm not going to do notes on Chapters 1 and 2. Most of Chapters 1 and 2 are covered in first year chem stuff. You can go on the Pre-AP Chemistry YouTube channel, rewatch that stuff. A lot of that was covered in our quick prep, the summer homework stuff. If you haven't finished those things yet, get those finished. This is a simplified version of what the textbook has. I'm going to put the simplified versions of the notes on Google Classroom. You have access to the full textbook through that Cengage login that you've been working with. For my distance learning folks, I am going to link the chapter readings to your OWL because then it can count towards your time for my class. If you're doing distance learning, remember you got to spend at least 4 hours of documentable time on my class or you don't get credit for being present for my class for the week. It shouldn't be hard. If anything, you're going to have more time than that because it's an AP class. We've got a lot of time on things. But yes, so Zoomdoll Chapter 3 is about stoichiometry. The first bit of this is not going to sound like stoichiometry. It technically is. The first thing we want to review is average atomic mass and how we find that. So average atomic mass comes from the use of a mass spectrometer, which is a device for measuring the mass of atoms or molecules. Here, by the way. Which brings me to another point. If you want to be able to write on these like this, download an app called OneNote. It's Microsoft OneNote. And then you can print these to OneNote and be able to write on them like I do. If you have a printer at home, feel free to print them, write on them all you want. But if you don't like paper, OneNote is good. Okay, so in a mass spectrometer, basically you shoot a beam of atoms through and they use magnets and electrical fields and you spread things out based on mass. We're not going to go into a whole lot more detail than that. It's a thing. It gets used badly in crime shows a lot because they try to mass spec things that don't mass spec. Remember what you see on the periodic table is an average atomic mass because different isotopes, like we've talked about already, have different masses. And we looked in first year chem at how to do percent, find your average atomic mass. Remember, it's a weighted average. So you're going to do percent times mass. When you do mass spectrometry, you get a couple different kinds of graphs. This is a little more realistic. Your quantities are determined based on the area under those peaks. This gets simplified into a bar graph for the sake of ease. Remember, if it's got, it'll either tell you intensity, peak height, basically you've got to calculate your percentages. If it gives you relative number of atoms and it's out of 100, remember anytime you're taking something out of 100, it's percentages. If it was relative number and out of something less than 100, then you'd have to do a little bit of math, but nothing too crazy. But the bar graphs are just another way of showing this. So how you may see this is given average mass, or given masses of two isotopes and their percentages, you can calculate average atomic mass. Things you should remember from first year chem. Remember that average atomic mass is mass times percent abundance plus mass times percent abundance. And you keep doing that until you run out of stuff. There are things that have like 5 common isotopes. So you just keep going. In this case, we're looking at a sample of copper run through mass spectrometer. It's got 2 masses we can work with, which is 63 and 65. This is one of those relative number of atoms questions, but since it's out of 100, these are percentages. Also remember, we don't want to leave our percentages as percentages. We're going to change them to decimals because that way our math will work out. So mass of our first isotope is 63 times our percent abundance as a decimal is 69.09 plus mass of our second is 65 times our percent abundance as a decimal, which is going to be 0.3 091. Before you even do the math in your calculator, which you're free to do here in a second, take a look at your numbers. We've got 63, a mass of 63 with almost a 70% abundance, and a mass of 65 with a 30% abundance. So if you think about it, think about what your number should be closer to. If you've got a whole bunch more of your 63, your answer better be closer to 63. If you had a whole bunch more of your 65, then your answer should be closer to 65. But also keep in mind your answer has to be between 63 and 65 because that's how averages work. Being able to estimate like that is good because in AP Chemistry, you cannot use a calculator on the multiple choice portion. So a little bit of mental math goes a long way. Hopefully you got that put in your calculator. Hopefully you worked out to the answer it's giving us, which again is closer to the 63. All right, so the mole, you should remember, is the number of atoms, a specified number of particles. Like a dozen means 12. A mole is always 6.02 times 10 to the 23rd of something if you've got a mole of it. We're going to use that in math. The nice thing is most of the time we don't actually need to know that. We just need to know it's a comparable number. But in AP, we do occasionally ask you to do that kind of calculation. And we call that number Avogadro's number. All right. Yes, there are ways to do this other than dimensional analysis. I stick with dimensional analysis because it's safer. If you want to look into the other ways, feel free. We're going to skip over the mole map because a lot of that stuff we're not going to talk about quite yet. All right, so refresher on dimensional analysis. Remember, you've got a couple of options when you're setting up dimensional analysis. Some people really like the vertical lines because it makes it a little easier to keep track of. Some people like fraction times fraction times fraction. Either way, you're putting what you're given top left. You want units to cancel. We're going to do a couple different examples. I'll show both ways. Remember, there's really no difference. It's just a matter of what you like the look of better. All right, so americium is an element that does not occur naturally. It can be made in very small amounts in a device known as a particle accelerator. Calculate the mass in grams of a sample of americium containing 6 atoms. So in this case, you should know that you are given 6 atoms. We just reviewed that what we're given goes top left. And so we're going to do fraction times fraction first. 6 atoms is top left, which means we also know we need atoms on the bottom. And remember, when we're doing dimensional analysis, when in doubt, we know we need to get to moles if we're not there already. And we just remembered that 1 mole is always 6.02 times the 10 to the 23rd. Particles and atoms is definitely an example of a particle. If you read your question, we're looking for grams. We're not looking for moles. So we're going to need to go one more step. We're going to need moles on bottom. And 1 mole for an element is equal to the mass of the element on the periodic table. And so the mass of a mole of americium, which is on the very, very bottom row, is going to be 243 grams. Atoms can cancel, moles can cancel. We're left with grams, which is what we want. A friendly reminder when we're putting scientific notation in the calculator, if you've got any kind of TI calculator, you want to use E. Some phone calculators don't let you, but if you have an E, it should be an EE key or possibly an EXP key. These are going to replace times 10 to the power of. That will treat this as a single number. So pause for a second, try putting it in your calculator, make sure you get this number. All right, so we can do the same thing, but backwards. which is exercise 3. Aluminum is a metal with a high strength to mass ratio and a high resistance to corrosion, thus is often used for structural purposes. Calculate both number of moles and number of atoms in a 10-gram sample. So this technically is a two-step problem, but you can really do it in one and just stop your calculation a couple times. So again, what we're given goes top left. I'm going to do the vertical lines this time. 10 grams of aluminum. We know we need grams of aluminum here. We know we're trying to get to moles as our first step. Remember, grams in a mole comes from our periodic table. So according to our periodic table, 1 mole of aluminum has a mass of 26.98. And so for our first answer, we just stop there. We're going to do our 10 grams divided by our 26.98 times 1. It also wants atoms. So if I've got moles up here, I also need moles down here. And we also know that 1 mole is 6.02 times 10 to the 23rd atoms. At least when it comes to elements. Again, put it in your calculator. Make sure you're getting these as your answers. All right. Try exercise 4 on your own. Pause for a second. Then we'll work it out. All right. Cobalt is a metal that is added to steel to improve resistance to corrosion. Calculate both number of moles in a sample of cobalt containing 5 times 10 to the 20th atoms and the mass of the sample. All right. So, again, we put what we're given, top left. And a friendly reminder, the 5.00 is simply showing us we should have 3 significant figures in our answer. AP Chemistry is not super strict on number of sig figs. Usually you get plus or minus a sig fig. Most of the time, if you round to 2 decimal places, you're probably okay unless you're working with really big numbers. We will touch more on sig figs off and on. I'm not going to be super particular about it as long as you're not going crazy with things. Most of the time, it's pretty straightforward. All right. So again, this one's moles and grams. You can set the whole thing up and just do it in 2 steps in your calculator. I've got atoms top left, which means I need atoms bottom right. We know we have to try and get 2 moles. We know that 1 mole contains 6.02 times 10 to the 23rd atoms. If I've got moles here, I also need moles here. And we know that grams in a mole comes from our periodic table. So for cobalt, that is 58.93. Atoms cancel, moles cancel. I'm left with grams. Again, you should be able to put it in your calculator. Make sure you get those things. All right. Molar masses. Molar mass. We've been doing molar masses for elements, which is just pull it off the periodic table. If it's a compound, we just add them all together. Empirical formula is going to be our lowest terms formula. We will deal with that more in our next set of notes. Formula weight. Don't freak out if you see formula weight. It's the same as molar mass. It's the same as molecular weight. It's a how technical are you being about things. Formula units are what you technically call a single subset of an ionic compound. Again, don't get too obsessed with it. If it's asking for a weight, it's probably just molar mass. Deal with it. When in doubt, go to 2 decimal places. It's probably going to be okay. Keep in mind that is not always the case on Quest, because Quest is the whole 1% error thing. Most of y'all are used to that by now. All right, so molar mass. It's talking about juglone, a dye known for centuries, produced from husks of black walnuts. Natural herbicide, yay. The formula is given. Calculate the molar mass. It's just add them all together. So because we've got more than one of everything, we just multiply the masses from the periodic table. Pretty straightforward, got covered in the quick prep stuff. We'll be practicing this a lot. It's just usually not the only question you're being asked. So we've got 10 carbons times a molar mass for each carbon of 12.01 plus 6 hydrogens times 1.01 plus 3 oxygens times 16. It's 15.999, round to 16. And that should get you this. Plug it in your calculator and make sure. Then we can just do dimensional analysis with that. Pretty straightforward. A sample of 1.56 times 10 to the minus 2 grams of juglone was extracted from black walnut husks. Calculate number of moles. We're going to put what we're given, top left. We know if we've got grams here, we need grams down here. We just found our molar mass, and that's in 1 mole. We're going to multiply, we're going to divide, which is basically just divide in this case. Again, put it in your calculator, make sure you get that. Here we're dealing with calcium carbonate. Same thing. It's just a slightly different formula. So, first step, calculate your molar mass. Past this unit, you're probably not going to be explicitly told just calculate the molar mass. Sometimes you are. Watch out for that on the short answer questions, because if they are nice enough to tell you that on the short answer questions, take the points. So you've got your calcium plus your carbon plus 3 times your oxygen should get you 100. Then we've got a sample of calcium carbonate contains 4.68 moles. Put what you're given top left. It wants the mass in grams, so start there. So 4.86 moles. Here we have moles. We're trying to get 2 grams. So 4.86 times 100 you should be able to do. That's your 486. But then it also wants the mass of the carbonate ions present in the sample. So you would still start with your 4.86 moles. If you look at your formula, this is your carbonate. There's only one carbonate, so you don't have to do much fancy math. 1 mole of CO3 is going to weigh just your carbon and your oxygen. So that's going to be 48 plus 12. So it's basically 68 grams of carbonate. That's a minus. If you had a formula that had more than one of your ion, you'd have to add an extra step to account for that, but this only has one. Again, plug in your calculator, make sure you get the answers given. And last but not least, isopentyl acetate is the compound responsible for the scent of bananas, and you can produce it commercially. And bees also release this. Yeah, the background on these, little wordy, not necessarily useful, but kind of interesting. Apparently banana scent can provoke bees into attacking. Watch out for that. If a bee releases 1 microgram, calculate the number of molecules, and then calculate number of carbon atoms. So we know we are given 1 microgram, which is 1 times 10 to the minus 6 grams. And we know we can go from grams to moles. How do we know how many grams are in a mole? We find the molar mass. We're noticing a pattern. So our molar mass is going to be 7 times our 12.01 plus 14 times 1.01 plus 2 times 16. That's a times. Get that math done. And you get 130.21 mass. Not sure why my keyboard says it needs to be there. And so that would let you find your moles, but it didn't ask for moles, it asked for moles. So this gets back to what we talked about with our mole. Okay. That 1 mole contains 6.2 times times 10 to the 23rd. Please go away. All right. Sorry about that. Molecules. Why molecules? Because what we're looking at is made of molecules. If it was a ionic compound, it'd be formula units. If it was we've been working with elements, so our elements were all just made of atoms. But if it's a covalent compound, it's made of molecules, and so that's what our representative particles are. That's what we have 6.02 times 10 to the 23rd of in a mole. So again, plug in your calculator, you get what they're giving us. Once we know our molecules, we could also calculate number of atoms. So this is telling us that we have 5 times 15th molecules. If we look at our formula, how many carbons are in a molecule? 1 molecule of this compound contains 7 carbons. So you take the answer you just got and multiply it by 7. All right, so that's a quick refresher on basic mole calculations. Work on your practice for that. Get help if you need it.